show the structure of this discussion. Give me 1 minute. Okay, so here is the structure. I will moderate the first breakout discussion, and then Nelly, Florida the second, and Philippe the last one, and Philippe then will close the team 4 and introduce at the end also the keynote speaker we will have. So let me stop sharing, and I would like to stimulate the discussion now, so feel free to answer. I will start with Sabine, Eva, and Gilda on the opportunities of the remote sensing technique you just showed to us. You already explained in your presentation, but in comparison with other remote sensing techniques, what is the real advantage, for example, in the case of Sabine, in using hyperspectral for natural hazard, if you want to compare this technique with other advanced remote sensing technique? And of course, I will ask the same question to Eva related to the seismometer, and Gilda related to the fiber optic. Please, Sabine, you can take 3-4 minutes to discuss this. Feel free just to take your time.
Yeah, morning and afternoon, everybody, and thanks, Paolo, for the question. It's a very interesting question. Well, me, honestly, I believe in a combination and synergy of different remote sensing techniques. And I believe that really each technique has its strong point where it provides something that the other does not. But at the end, let's say, for example, I know it for volcano research, it works by combining the different information. So for hyperspectral, it's very clear it's this capability for material identification, and that we are able to differentiate different types of, I don't know, I'm not a geologist, so this is where maybe I don't use the right wordings, but different types of lava flows, because I know I was speaking with Thomas Walter to make a project in Iceland where we would bring, but it was always the limitation of those airborne hyperspectral campaign. I know over Etna you had some, but we had the idea of going over Iceland and bring a hyperspectral imager to look at these different lava flows or pyroclastic. Sorry, I'm not like a person on volcanoes. So here, this is where I'm vague. But basically to see if we are able to identify different geological or lithological differentiation that can help you guys to make some, I don't know, with whatever you are doing on your research. And me, I see the input of hyperspectral in that, lithological differentiation, some geological mapping, also the type of vegetation, because sometimes it's also a symbol of the underlying structure, like maybe the type of vegetation that grows on the earth, maybe changes there, which is a sign that something is happening below it. This has been also sometimes used in some studies, like soil salinity impact. Okay, this can be some other type of hazards too. So I see hyperspectral in that. And the thing with hyperspectral is that it is not available every week. So anyway, hyperspectral, it will be like this one or a few hyperspectral acquisition over the area of interest, but has to be combined with more regular monitoring of another methodology anyway. But hyperspectral will be able to provide an assessment of the status of the surface, really in terms of biochemical and biophysical parameters. But I believe, honestly, the other techniques are not providing.
Yeah, and it's interesting what you said about the combination with other techniques. For example, I'm asking if, just to show to us or to mention to us an example of a combination of hyperspectral data with, for example, other kind of data. I would like to say, if you're using hyperspectral for vegetation, I think you can use also LiDAR, maybe together, to better understand the vegetation height with the vegetation type, to improve the differentiation, the classification of different kind of vegetation.
Yeah, it's a good example. Hyperspectral LiDAR is one avenue of big research in the future because of this combination of this chemical nature information from hyperspectral with all the height and structure from LiDAR. So this is one very good example. There are examples, because I'm maybe more specialist on soil research, combine SAR with hyperspectral, because SAR will provide information on the soil moisture, but a different layer, because hyperspectral provide information on soil moisture at the very top, maybe 1 centimeter or less, and SAR will provide the soil moisture at different depth. And to characterize soil roughness, so we could characterize different types of clay with hyperspectral, like smectite or illite, whatever. And with roughness from radar, we can identify rough versus smooth soils, things like that. So this is another example. And another example, maybe I can mention a study in Namibia. We were looking at salt pans, and it's synergy multispectral with hyperspectral. Because with hyperspectral, we had one Hyperion satellite hyperspectral imagery, where we characterize very well the quantification, which salt, how much percent gypsum, halite, was on this pan. And with the time series, 30 years time series of Landsat 8, we were able to characterize this water cycle in these salt pans, in these flooding, retracting events. And this made a very nice study where we could infer some deductions on the salt pan cycles and the surface processes in the region. So the combination of both. Thank you,
Sabine. Very interesting. Now I will just ask the same question to Eva. So please.
Well, so if you just think about seismic waves and the wave equation that describe these seismic waves, you will notice that these waves do not just have a translational component, but also a rotation. And even if you think of some waves, like some love waves, they will create some shearing and some rotation in the ground. So in the past, the rotational part was just ignored based off a lack of instruments that could record it, and the argument was that it's not as important as just focusing on translation. So now that the first instruments were developed, first not portable instruments to record it, the importance was kind of risen for the rotational component of the wave field. So I think it is important to extract as much information on the waves that we record as possible in order to enhance our understanding on the sources or the processes. So I think it is necessary to use these sensors to record the rotational motion as well, because it can help us to understand these processes better. And I mean, if I think of the ongoing eruption in Iceland, I had some colleagues which then carried like several seismometers plus batteries for each seismometer across these very rough lava fields in order to install arrays and things. And it is just easier if you just have to go to one location with your like rotational sensor seismometer, and you can extract the same information. Of course, like in seismology, we also talk about like high resolution. So we're sampling the ground at high temporal resolution. But of course, the downside is that, well, we have 3 components, but it's just from one point, right? So in a way, it's nice to compare it to like some DAS measurements where you have more measurements along a distance where you can like spatially record the wave field at higher resolution. But for me, if it's like a location which is very difficult to access, such as some very remote volcanic environments, or if we talk about, for example, these expeditions to Mars, right, where you have limited space in the shuttle, and you might have space for one sensor. Of course, ideally, that's a sensor that can record the 3 translational motions, but also the 3 rotational motions, so that you can have a very good measurement of the wave properties that you record in this like extraterrestrial planet, for example, or at the ocean bottom. So yeah, Philippe.
Yeah, may I intervene here? I like your example of on Mars because but on Mars there is no real natural hazard. So I will be quite picky here and ask you, well, okay, fair enough, that's interesting, but what does it bring to us to know this kind of rotation? Does it bring something more for seismic hazard to be able to measure the rotation in complemented to the translational movements?
Well, I mean, if we talk about some very mountainous regions with, for example, hazards such as landslides, these are very difficult to access or to maintain instruments in this region. And if I have to maintain like 20 instruments there, this is more of a problem than if I just have 10 stations. And for example, usually it's not just the installation, but it's also the maintenance of the instruments. So if the instruments fail, or you need to change batteries or solar panels or whatever, this is more easy if you just have to access 10 locations and not 20. So this is where I see the advantage of like rotational seismology, and it is a very new field. So the sensors were only developed in 2016. So now we're basically moving towards the first field experiments, and a lot of these field experiments were on volcanoes currently. There has been an installation in Greenland on the ice, but this is not published yet. So this is really research in progress. But yeah, I think in these areas where it's difficult to, where you don't have much space actually to install something wide-ranging, right, like an array. You don't have a huge area that is planar because it's all steep mountains. So then it is very cool because you can just use like one point, one good point that you have in that area, install your rotational sensor and seismometer and do, extract information on the ground, on the wave field. You can track your motion, right? So this is a huge advantage. And with an array, you need a plane area. They all need to be the same height, or you need to correct for that. And like I said, if you have a failure, you will have a failure of stations or of some parts, components of it, linking it. Then you need to access all these locations. And I think it's very good if you have to, access less locations, because you need less personnel, you need less equipment, less cables, less batteries. So this is, in my opinion, the benefit of using a rotational sensor that it can bring for monitoring natural hazards.
Thank you, Eva. Thank you, Philippe, for highlighting that point. Now, let's give some time to Gilda to provide her reply on this.
So the advantages, as I show you, are several. Mainly, we can use existing cable in submarine area, which are not so accessible for traditional application, for traditional monitoring methods. And we do not need to deploy any cable. If the cable already exists, we just have to go in a place to access the cable, plug and play, just 1 hour of deployment in a remote area. We don't have a problem about solar panel, batteries. If the site where the cable is accessible, there is power supply. So the cable itself has a long life. So from maintenance point of view, we do not need to care about the cable so much, because the cable are strong and can stay for long period. For example, at Etna, after we installed a dedicated cable in 2018, the cable is still there. So anytime we want, we can go there, and we have an availability of 750 sensors all at once. So we just need to plug the DAS and start to interrogate the cable and acquire the data. From a research point of view, I think that the advantages in the area that I know better, which are seismology and volcanology, are several. Mainly one, the high spatial sampling. So we can monitor very localized phenomena. so we can better understand default response, default behavior. So this kind of application could be very helpful for near fault observatories, because with classical instrumentation, we cannot have a fully overview of the response of a fault, because we don't know exactly where the fault is. We can map better the fault, we can study its response, and not only at high frequency, but also at very low frequency. So the response of the fault to several sources. Regarding volcanoes, what we have learned from the experience done here at Etna is that we will be able not only to look at the I say seismological phenomena, but we can also push to see phenomena going toward low frequency signal, which are helpful to understand when the volcano is almost ready to go to unrest. So try to understand the ground deformation which precede the unrest, and monitor the slow inflation of the volcano, not only at one point, because at this moment there are several instruments that allow us to monitor the ground deformation, but both GPS and satellite have not enough accuracy to see very tiny ground deformation on the ground, which precede, for example, this kind of unrest that we are seeing at Etna, like lava fountain. So this unrest cannot be monitored by this classical geodetic network. This tiny phenomena could be monitored by strain meter or tilt meter, and in such a way fiber optic measuring strain rate have a very high accuracy to complement tilt meter and strain meter, which has just point sensors. So we have just one point on the volcano, and we are not able to locate the source and have information about the source property, because with only one point and using the classical geodesy theory, volcano deformation theory, we are not able to locate the source. So having more point, we can make a step forward toward this direction.
Thank you, Gilda. Thank you very much. Philippe, you have a question, maybe?
I have a similar question to Gilda than the one I had for Eva. You're say, well, I will be the bad guy here.
Yeah, sure.
You seem to say, well, this is fantastic tool. How do we get access to interrogator? Is it easy? Should we rent them? Should we buy them? What is the cost? I mean, these are practical questions that people could ask for. And I would like to tell the audience, please ask questions, be proactive, and don't hesitate. I just saw also that Kuo-Fung Ma just arrived. Hello, Kuo-Fung. Thank you to be here, and we are going to talk later together. But if you want to intervene, please go for it.
Thank you.
Okay,
about interrogator. So interrogators since a couple of years ago were not indeed available. So the factory developed by themselves and just give the possibility to research, to use them, and that's it. But nowadays, several companies started to sell them, and there are several companies which are on the market developing new interrogators with even better performance. Nowadays, the costs are still high. So to buy an interrogator, you need hundreds of thousands euros. But we hope that in the near future, the cost will decrease in a way to allow people to use them more. We have to remember that this kind of technology was firstly used in oil and gas industry. So for them, it was not a really issue to rent or buy them. From research, naturally, we have to find funding to rent or buy some of them and use.
Thank you, Gilda. I will ask, of course, to the public if they have some questions. Please don't hesitate.
I have a question.
Yeah.
I have a question on the spatial resolution of the spectral methods, because, for example, in geothermal area, mineral deposits are interesting to study, to see how the fumarole evolves. So usually this kind of anomaly are very localized. So my question is, which is actually the spatial resolution in detecting this kind of for mineral deposition, for example?
Yeah, I can answer you. Let's say the satellite, so NMAP is a 30 meter. So it's kind of coarse, well, but it's not so bad even. If you have a chance to have an airborne campaign, of course, you can reduce this to 1 or 2 meters. So we have nice research projects with airborne campaigns too. But of course, then we have to, ask the money for the flights into the projects. But this is fine. We have done it on flights in Africa, in several countries like this. But on the other hand, what I wanted to say is that my experience is that we detect things that are much smaller scale than, where we detect changes, where you are in the field, these changes are much smaller scale. It does not have to be 30 meters, because this is an advantage of hyperspectral that you can unmix. This is what we say, the data. And finally, at the larger scale, we see changes that are happening at much smaller scale. That would be a bit my message here, not to extrapolate. If this is smaller than 30 meters, then we cannot do it. No, we really see things that are much smaller scale. But there will be some limits, obviously. Yeah.
Thank you.
Okay, just a few minutes before moving to the session of Nelly, I would like to ask something related to cost. Already you will discuss about this, but especially to Eva and Gilda. The number of sensors, for example, in the case of Eva, the number of seismometer, you already told us something. And also in the case of Gilda, the number of the density of the optical cable, for example, for monitoring a deep-seated landslide. So I fully agree that the optical cable will be the future, especially for a better understanding the movement of a complex landslide system. But what about how much? What about the density of the sensor we need to provide in order to fully understand and from the spatial point of view, the phenomena? Eva first, Gilda then.
Yeah, so I think it depends on, like if for example, we're somewhere in a mountainous area and we would like to monitor a landslide. If we just want to have like an early warning system that detects like these migrations or these signals and then estimates some speeds, for example, if we know the pathway, I think one sensor is enough to get a direction and then intersect that with the known, for example, flood path. Like floods always drain along the same flood path, so glacial floods. So then one sensor is enough. Of course, if you want to do some like beam intersection, then two would be ideal, or even 3. But I think we can definitely reduce the number of sensors, and we have to if we're talking about the cost as well, and then also potentially accessibility of a region. So I think if the region is very difficult and inaccessible, I think you can already do quite some research with just one sensor on one rotational sensor co-located with a seismometer.
Thank you. Gilda?
From a fiber optic point of view, I think that this could be arranged depending on the area that you want to coverage and the localized phenomena. Because with fiber optic, we have no problem in densification of point, because we can have a spatial resolution of 2 meters by itself or even lower. There are some devices using the Brillion, so mainly for measuring static strain changes, which are also 40 centimeters. So the main thing is to understand how to cover the area, so how long the cable should be with respect to the resolution you want, because it's not a matter of deploying many sensors. It's just a matter of how long the fiber should be. And in case of landslide, I've seen a very nice application using this grid approach. So indeed, it's not just a measure along one single line, but along a matrix of point. If you want to configure the fiber optic in a matrix configuration, so this is the main point, because it does not need then more work on the deployment.
Yes, thank you so much. And the cost, just
so about the fiber. So fiber cable, so there are several fiber cables, so mainly for dynamic strain changes. So I mean, DAS application, you can use just telecommunication cable. So cable used for transmit data. The average price is €2 per meter, more or less.
Okay. For you, Gilda, there is a question. You're able to, from the public, from our
yes.
The people are following us, if you are able to reply.
Yes, sure. So the question is how to validate the DAS observation closer to seismometer, acceleration or velocity. Indeed, this was the first experiment that we did on Etna. So we deployed a fiber cable on the summit area, and then we deployed several seismometers, geophone and broadband seismometer, all along the cable. So what we did is to transform the seismic wave field in strain using several methods, and compare the strain derived from the seismometer signal with the direct strain recorded by DAS. And there are several approaches that could be used to make this comparison. We have used several of them, and the match between direct strain measured by DAS almost matched quite well with the strain derived from seismometer.
Okay, thank you so much. I think we just finished. Oh, okay. There is another question related to, okay, from Leonardo Acque. My question go, young journalist of geophysics. Leonardo, can you please re-explain a little bit, because it's not clear the message you left in the chat. Leonardo, let me give. You can talk, Leonardo. I gave you the right. No, it's not speaking. I'm not sure, Philip, Nelly, if we are planning to answer to Leonardo message, but it's not.
It seems that Leandro is trying to find a path for his studies.
Yeah, but
So it's not really the topic of
exactly.
the session, but I mean,
Okay.
all maybe there are some answers possible from to, or if Leandro would like to speak out.
Yeah, indeed.
Leandro is very quiet, so he's very shy. Probably it's not
Okay.
not a problem.
Okay, maybe he can just
So
write to the speaker asking
yeah,
more directly about this.
maybe the question is about the how to study this field that we are gathering for natural hazard. How can we study this? Is there schools? Which direction should the young people go to work in these directions? Maybe this could be translated like this as a question.
Well, I think you can look at the natural hazards from a different range, and I think that's also the benefit. So you could, like I think you do study geophysics and then learn some methods in geophysics and apply it. But then, of course,
Yes.
you could also span like some more remote sensing techniques to like ground-based techniques, or talk to like volcanologists or geologists about processes, landslides, volcanic events. Whatever might be of interest, because I think especially the discussion among disciplines is the one where you can gain like a lot of interesting insights into the processes, because we all have like different ideas about these processes that happen, and bringing that together can help to further the understanding of these processes.
Yes, thank you, Eva. I think now we just conclude the first slot of discussion, and I will give now the next slot to Nelly Florida, who will moderate this. So please, Nelly, now the theater is yours.
Thank you, Paulo. First of all, I want to express my highly gratitude to all the speakers, and all of them are ladies. So I'm really proud of. And also also our keynote also lady. Wow. So it's very good for us. So my part is about the talking about the novel in situ monitoring approach. Maybe I will start with the as I'm from Indonesia, we have experience with so many natural hazards, from earthquake, tsunami, landslide, flood, and even tropical cyclone. So what I want to highlight is in Indonesia as a very big countries, but more than 60% consists of waters, and 17,000 of island. So we really realized that how the in situ observation is not easy for us, because it's related with how we can build or provide good infrastructure in the region. Even in the remote area, we will must consider about the electricity, road access, communication, and others. So talking about in situ monitoring, so what we want to discuss with the speaker, how we the challenges of how we could find a better solution for our observation. Let's say Eva already mentioned about the rotational seismology, and of course how how we can move forward with very and very new technology, and can apply in a country, let's say like Indonesia, with so many natural disaster. So I want to have your opinion on that. And I think I will start with Eva. Please.
Yeah, I think the advantage is that, of course, from like you can detect signals from a safe distance using a seismometer. Like for some of these floods, for example, if you wanted to monitor them using, I mean, like okay, let's talk about an application I have in mind in Iceland where you would have like hydrological sensors or GPS sensors on the ice. But with like a seismic array, for example, you could detect and track these floods from like 50-kilometer distance. So if you have multiple potential sources, you know, it might be able to detect and track them from a safe distance if you're limited, if you cannot get very close, if you're limited to roads or access to regions. With a rotational sensor, like it still has to be proven, like you know, how sensitive it is. I mean, it depends. It's a trade-off of distance and source strength. So if your source is very strong, of course, you could be at a further distance. You could install your sensor, and you know it's still fine. If your source is very weak, then it might, you know, it is a problem for the rotational sensor because it's not as sensitive as a seismometer. So I guess, you know, then for these kind of installations, you would need to sit down and talk about signal strength across the frequency band to decide how close we actually need to be in order to detect this signal. But even if you're not sure, like from which direction this landslide might happen, right? I mean, it's still like rotational seismometers might help to determine this this direction or like changes in direction or migrations as well, and you can use that to estimate maybe some speeds or actually just detect the signal if you have like a change in direction, because this relative changes, you know, these are reliable. If you think about the seismic networks and like location, amplitude-based locations, you might, like there might be a bit of movement, but it's unsure whether this is just within the uncertainty or whether this is really a true migration of the source. With a rotational sensor, if you calculate the direction, like it's a very simple processing, you can do it in real time, it's very fast. And if you detect a relative change in this direction, well, you know that your source is moving, and you know, you can use that to track your landslide, your flood, your lava flow, your lahar, you know, whatever it might be.
Thank you, Eva. I will continue with Gilda with the same comment that I as I have introduced you. Imagine like in our the country like Indonesia with so many natural disasters. So how we can have like an in situ monitoring approach from your perspective about the fiber optic sensing. I still you need the in situ monitoring to combine with this kind of equipment.
So for this kind of method, we need two objects. We need a fiber cable and we need an interrogator. So the first thing to do when you want to deploy such a kind of measurement is to decide which area you want to investigate and what you want to monitor. So, for example, if you are interested to monitor a fault, you can see if there are telecommunication cable already present in the area, and ask to the telecommunication provider the accessibility to this fiber. This is what we have also tried to do at Etna. So we called the telecommunication provider, asked them about the map of the cable already deployed in the area, and then we selected the fiber cable crossing the main fault. In this way, you are almost ready to start your measurements, so your in situ monitoring. And then you need an interrogator, have the access point to the end of the cable, because for DAS equipment, you do not need to interrogate the cable both sides. You just need to plug and interrogate the cable from only one side of from only one end of the cable. So you need to deploy to install the interrogator, which is just like a computer case, so very small device, and locate in a safe area and start to the measure and record the data. If you have not the availability of cable already installed, you have to do the big job to install a new cable. So it means that you have to have funds to do a small trench and deploy the cable. One thing that we have confirmed in the experiment done, not only by our group, but also by other groups involved in this kind of activity, is that we do not need to do big trench. So what we have found is that the coupling between the cable and the soil is easy to reach. So you do not need to do a trench 1 meter depth, but just a few centimeters is enough to warrant a good coupling between the soil and the cable. Then if you want to measure some particular thing, you have also to take into account that this technology records the strain along the fiber. So it is axial strain measurements. So when you deploy your cable, you need to have the maximum signal to noise ratio. So it is better to deploy the cable in a way that the direction of the cable is along the main signal you expect. This is just a couple of advice in doing these measurements.
Thank you, Gilda. How about Sabine, that on you talk about hyperspectral remote sensing. As I know, in our country, we use it for the food security and also for mineral exploration. But I think this kind of monitoring need very good validation in the field. As example from my experience, for food security, we need automatic weather station in the field, so we can include the data for analyzing what we have from this method, from the hyperspectral remote sensing. How do you think?
Thank you, Nelly, for the question. It is actually very important. I did not mention this at all in my talk, and actually I was just writing a question in the chat about the combination of in situ with remote sensing. We actually all these fancy hyperspectral remote sensing studies, we always have in situ measurements. We need to send teams to measure, to put some types of, let's say, calibration for our models. And so we need to make a sampling of the ground, both of the vegetation and the soils. It is actually quite heavy. And I think maybe more and more we will evolve that we have enough maybe global in situ data. So the link with also global databases is very important. Maybe at some point it will evolve so that we will need less in situ data, but I believe personally we will always need a bit anyway, and it's important. And for me, it's also the question is somehow we can always deploy those teams, and we have always to speak with the farmers or with the landowners.
Mm-hmm.
And then there's also all this technique equipment that we have to carry in the field, which also makes it complex, and we cannot access everywhere. And for example, for the vegetation characterization, it's always very, very hard. We need experts, biologists to be there. So it's big teams actually in the field. And I was a bit wondering also on the presentation of Eva, how all the one on the fiber optics, like how these measurements in the field can, I don't know, help or support or provide a different information than the remote sensing. And it's all this combination of techniques, which I think is interesting, but it's not so easy because we have to think of the right combination that provide the right answer. Or maybe it's not the same combination of technique that provides the best answer for each natural hazard. So I know it's very wide. Sorry, I'm not providing any clear answer maybe. It's very wide thematic.
Okay, thank you, Sabine. Yeah, I have one more question for Sabine, because like in Indonesia, we are area with have a very strong convective. We all of our all area of us covered with cloud. So how can we use this hyperspectral remote sensing to?
Yeah, okay, this is actually an important point. Well, it is optical remote sensing. So if really you have a very, very high cloud cover, basically, maybe this is not the best technique for your area. Because I remember once when we talked about volcanoes, we talked about these people who work in Kamchatka, and we kind of all agreed that optical remote sensing was maybe not the technique to use there. So yeah, it's difficult because we really have a requirement on the cloud coverage. And if there is too many clouds, we just don't see the surface and the signal then is not useful. Yeah, this is a limitation.
Yeah, thank you. Gilda, you want to add something, please?
About coupling the spectral analysis and the fiber optic. Indeed, about fiber optic, there is also another area of research in fiber optic, which is fiber optic chemical sensing. So what they do is essentially use the fiber to sense the variation in chemical species. So there are some particular devices which are able to measure the variation of the environment in terms of abundance of some chemical species and give information about their variation. So nowadays, I've seen in literature, there are some methods which are able, for example, to monitor H2S or CO2. So with a very high spatial resolution as the fiber optic methodology is. So these kind of measurements maybe in the future could be coupled with hyperspectral analysis to monitor in real time, which is the evolution of the ground itself.
Yeah.
Thank you, Gilda. So, are there any questions from the audience? Oh, we have Sigrid. If you want to speak up, please. Alice.
Yes, I can speak up.
Okay, thank you.
I was just giving a comment on the answer still to Sabine, because in the hyperspectral case, like Sabine already has explained very nicely, we mostly go about lithology. That means solid Earth. And solid Earth is usually not changing that quickly. So, and since the NMAP mission, the future NMAP mission, for instance, is a tasked mission, so it's also possible to try getting acquisitions in areas which are more often covered by clouds than others. And the big advantage is also that we can combine such hyperspectral acquisitions with multispectral acquisitions and also with radar acquisitions, and with the Sentinel missions, which have been going on now for quite some time, already the past 5-6 years. We have a great opportunity for future combination of hyperspectral data acquisition with these acquisitions, which allow us much more process-oriented monitoring. And that can be applied to many things like volcanoes, like landslides, also floods. I mean, yeah, there is a big potential in the future, also because we already have a quite big archive of globally available Sentinel data, which then later on can be extended by hyperspectral data acquisitions as soon as globally acquiring instruments will be in space. And that will not only be the NMAP missions, there's an Italian mission already now, and also the US is planning missions. Sabine knows much better than I am. I mean, hyperspectral will come at a global scale.
Thank you, Sigrid. Do you have any comments, Sabine?
Yes, Sigrid is right. I should have mentioned it. So NMAP, and actually there is an Italian mission. Sorry for my Italian colleagues. I didn't want to not to speak about it. There's a Prisma mission that took off already 2 years ago now. So actually, if you want to make some test research, you could already request hyperspectral spaceborne images from the Prisma satellite. It's also free of charge and data, open data policy. So NMAP will come next year. So that means we'll have more data, because the limitation with hyperspectral is this only once per month revisit rate. And with the cloud cover, then we have to have just this 1 month revisit rate just on the day where the weather is nice. So finally, we have a test field in Germany, and we have 4 images per year that are cloud free based on Prisma. So I think we can expect that in the future, except of course in desert region, where we can expect that we have more regular monitoring. So when there will be Prisma plus NMAP, then we have access to more data. But then in end of the 2020s, we have to look via ESA and NASA missions for operational hyperspectral that are in preparation. And operational, it means it will be like Sentinel-2. It will be a Sentinel hyperspectral. It will be a Landsat hyperspectral. And those missions will come 2027, 2028. So hyperspectral will become more and more affordable. And in a couple of years, we will all have hyperspectral data over all points on Earth. So this is something that we have to see for the future. It's a good point.
Thank you very much. I think I just have one small question to Eva, if we don't have any from audience. Because you mentioned about the rotational seismology, I just want to ask your opinion, because for our case in Indonesia, we are very active of tectonic plates. So how do you see in the future that apply of this kind of technology in Indonesia right now, because we are improve and develop our seismology network, seismic network nowadays?
Well, so I guess it's like a seismic network that you have on the islands, or do you have some ocean bottom seismometers as well that you use? And yeah, well, I think so. There are currently some rotational sensors developed as well that can, be deployed on the ocean bottom. So they are like watertight. And I mean, these can be added to the ocean bottom to help, for example, with the orientation of the seismometers or the tilting, and that might help to characterize these earthquakes better, that might generate tsunamis, for example. But of course, even on land, if you add a rotational sensor, you can study the sources better, or migrations more easily. So if we talk about some natural hazards that might occur, or volcanic eruptions, or forecasting, I think this can be very beneficial to actually record the rotational ground motion as well, and not just ignore it. Because, like I said, some seismometers are sensitive to tilting, for example, and you can only find out whether your sensor has tilted, or you might need to correct for it if you have some rotational measurements that are independent to translational motion, and that you can then use to correct if needed.
Okay, thank you, Eva. If are there any questions from the audience? Oh yeah. Okay. Thank you.
I would have a question, if possible. I would have a question to the fiber optics. If you monitor a landslide with fiber optic cables, to what extent can you get three-dimensional information, or are you getting more information, for instance, about the deformation at surface or at the depth where you put this cable in? So if you could explain this a little more, what is actually possible with these cables?
Yes, so what is usually done, usually I mean in the last years, is to use some grid or matrix, so you can monitor the deformation over the surface, but meanwhile dig a small drill in which you can put the fiber inside. So in this way you can also monitor the vertical deformation. So from a grid at a certain point, you can decide also to make a hole and monitor the strain along the vertical direction, installing the fiber also vertically. And you can decide to do this in several points of the grid, configuring the fiber, so the matrix and this hole in advance. This is what is usually.
Thank you.
Yeah. And can I have one follow-up question very briefly? Is that, has that been used also in combination with radar and INSAR? Because I know the INSAR techniques has been used a lot for spatial deformation monitoring at surface, and they're combined, for instance, with GPS measurements, but in part also inclinometer measurements.
Yeah.
Do you know similar studies already with optical fiber cables?
Yes, about landslide, there is a group indeed in University of Padova at CNR IRPI, in which they are using and they are making a lot of experiments using fiber optic for landslide and hydrology application. And the group of Luca Schenato, there are several papers already out about the use of fiber optic for landslide monitoring. The advantage with respect to INSAR data is that you are a continuous monitoring. Instead, at this moment, the INSAR is every week, every 6 days. In this way, you can have a continuous monitoring and then a very high resolution, because indeed you are on the ground. You have no problem with other backscattering problems, which usually occur with INSAR data.
Okay, thank you, Gilda.
Thank you very much.
Thank you, Sigrid. We met tomorrow. Yeah, we have met yesterday. Thank you, Ms. Fongma, for the suggestion that to deploy a more low-cost, high-performance sensors, pilot strong motion sensor with broader band. So we have. Can we have just this one question, Philip, before your turn?
No problem. Please go ahead.
Okay. It is, I think it's for Gilda. Zigzag deployment of fiber cable effectively aid to more dimension.
Yes, indeed. If you change the orientation of the cable, you can have the strain measurements over several directions. Yes, so this is again about the geometry configuration of the cable when you want to use it. Yeah.
Okay, thank you. I think this include we can conclude this second part, and please Philip, you can continue with the third part. Thank you.
Thank you very much, Nelly. for very interesting discussions. I hope we'll continue the same. There are still many questions, and we are going to try to continue now. So yeah, the session is more, we already talked about it a little bit before, but the future of remote sensing and monitoring, basically on all these objects that we are dealing with. Yeah, so but some questions like what is missing, what is the future of remote monitoring? So maybe we can, we are talking about the future, but just before talking about the future, we talked about fiber optics, we talked about rotational seismometers, but these are new equipments, but there are also conventional measurements that are still being used. Is there still a future for those techniques, and how to use them? So maybe Sabine, you can start with this, and then Gilda and Eva, about very shortly about the conventional techniques that are used. Are they still more accessible than the new techniques, and what are the benefits?
I'm not sure. I will make like a yes/no answer. What we see in hyperspectral is a development of databases in the laboratory of spectroscopy, so spectral data. And what we see right now, or since actually a couple of years, the development of standards and protocols so that everybody around the world is really international groups. And a part of one is the IEEE Standard Association groups, where we develop standards for the acquisition of spectroscopy in the lab and in the field. So that means we are, the aim is that we develop those global databases so that in the future, or even now, if someone has got a hyperspectral acquisition, or it can be from Sentinel-2, it doesn't have to be hyperspectral, but basically using those databases, they can calibrate the model and estimate a thematic parameter without having to use fancy algorithms that are non-available to everyone. So I think I see this, the development of the databases. And I see lots of research is now already done based on current satellites, but now we see it is still the case that people are specialists in one technique and do the one technique, and we still maybe something that can be better done is this combination of several techniques in maybe one observation object, let's say. To really advance on actually the process, like the process observation and modeling and what it can give as new information about the process, actually. Maybe something we can work now.
Thank you. So Gilda, possibly about the conventional strain measurements. Are they useful?
Yes, so with the seismometer, we have talked already, so the comparison with the seismometer. So another interesting thing is to compare with the traditional strain meter. Indeed, the strain meter available nowadays are very accurate. So the accuracy is on the order of 10 to -10. And fiber optic sensing is going toward this accuracy. But with respect to a single point strain measurements in a boreal, the fiber optic sensing give us, as we said, much greater opportunity to monitor the ground deformation, even if we have to cope with other problem that we already almost know, because fiber cable is also affected by temperature as the strain meter are. So we have to develop algorithm to remove temperature variation generated by thermoelastic effect. So there are many things that could be done, and it is interesting nowadays to make this kind of comparison, because the aim is to validate the new technology, so the fiber optic sensing technology, and meanwhile do a step forward, new monitoring method that could advance the understanding of natural hazard. And then when we have understood how the methodology works, we could also easily apply for continuous monitoring. So this is then the final aim.
Eva, a short comment?
Yeah, I agree with Gilda. I mean, we have these monitoring networks in place, and the new instruments that we develop now can, of course, be tested against these networks. Of course, if we talk about like monitoring, it's very important to have this database of like past events so that we have some kind of benchmark we can compare new events against, and to maybe help our like fast interpretation and understanding of these. So I think it's very important to also keep the instruments running, the seismometer networks running, because I think they're very beneficial. There are a lot of automatic like locations or analysis like based on these networks, which are of course used in the monitoring in order to estimate the status of the volcano or the stability of the slopes. However, I think that like stepwise these should be improved by adding like more analysis, like to have maybe arrays in the field and do array processing, and add that to the other observables that you have. Or then if we figure out that it's very beneficial to have rotational sensors because it can lead to more like a more detailed resolution of the source processes of these events. Of course, this should be added as well. And then I think it's actually important to try and get the real-time data processing up and running and classification as well, because only then this like monitoring will help, or it will be very beneficial for to be included in the monitoring, because then you have people 24/7 who look at the data streams, and if it takes half a day to download data or to do the processing, then of course this is too late and won't be added in real time. So I guess this is an interesting thought as well, to see whether these new techniques can add benefits, but then actually add benefits in real time as well, if because this is necessary if we want to do some monitoring of real-time monitoring of natural hazards such as like landslides, avalanches, floods, volcanic eruptions.
Thank you, Eva. Yeah, that's very true that we should do this. So this raises two questions that we will address afterwards, is data processing. First, I would like to take a question from the audience that Nelly forwarded to me. And so with remote sensing emerging as a mainstay, I don't know what as a mainstay of disaster risk reduction and management studies, what are your thoughts on making data publicly available? So this is one question about putting the data available on the community, so that, and then we are going to talk about data processing, because maybe the people may have the idea on how to process the data and bring some new ideas on this. So first, how to make the data available, and so that, well, the community, scientific community can access to this.
Yeah, I think the question is also very much important for the networks or people who have in situ data, because in satellite it became more useful, and now, well, now several satellites provide their data for free. So, but of course the data don't fix the problem, but okay, it's another. Then the data processing, so it's the next question. But I think the networks, some networks already provide all the data for free, but some others don't, and each time it's a big issue. I agree. I think it's a question of funding. Also, some people spend years developing the database and don't really want to give away everything.
But when the data is acquired and with public money, there is this new fair approach of data management, which is foundable, accessible, interoperable, and reproducible. This is a new, very important way of dealing with data. Is the remote sensing satellite data available like this? Yes. There are many websites where you can find the INSA images, for example. And
yeah, right. I think TerraSAR-X, you have to ask. Okay, I'm not specialist on radar, so
no,
maybe
but
somebody
was
else
just
can
an
answer
example.
it. But Sentinel, Landsat, it is all free. They
Yeah.
are downloadable tools on the web, and this is true actually with ESA, NASA, and the big agencies. Now we almost do not discuss anymore the free availability of the data, because this is what they already do. But now everybody is discussing that to have data that people can exploit. Because putting the raw data on the web and charging people with the data is actually not helping finally. So the data are available. Yeah, for all the Sentinel missions, this is right. This includes the radar missions.
Yeah, Sigrid is giving a link for the Sentinel.
I mean, the Sentinels are actually exceptional. I mean, everyone who wants to get started or maybe get a better idea about the potential of optical and radar remote sensing should visit these ESA-hosted web pages, because it's not only the archives, it's also tools. It's also very easy to click visualizations. It's just amazing. I mean, everyone now can get a feel for the capability of remote sensing data and on the fly combine also radar and optics for any given area which is covered by these sensors. I mean, if I want to check out data acquisitions for other sensors, I go to the Sentinel archive and look in a very easy calendar on which days I have cloud-free acquisitions. And I must say this is really great. And also to mention another in terms of near real time is Planet. Maybe you have heard about the Planet Lab mission. And these are mini satellites, hundreds in orbit, and they have been acquiring data regularly since 2016. And now every point on Earth in daily coverage, 3-meter resolution, multispectral. And it's not completely for free. However, they are very generous in supporting science and also education. So if you are affiliated with a university as a professor or so on, you can get quite a nice quota of data supporting any kind of master and PhD project, for instance. So the Planet data bring us as close as possible right now to a more continuous monitoring. So that's why they should be very much also considered in combining remote sensing approaches with in situ approaches, which are much more capable of providing continuous information. But this will be a new level than also having spatially covering high temporal resolution information, which I think will bring the combination at a new stage.
Thank you very much, Sigrid. That was very useful. I guess there are similar things for seismometers. Eva, you may say a word on this. And then Gilda, is there any such capabilities for fiber optics?
Yes, so there are databases where people can access seismic data around the world globally. There are some seismic data in networks which are just streamed to these databases, so they can be accessed in real time as well. But there's still, in my opinion, a move towards making all sensors available, and it takes time. Sometimes it's just published data is published with alongside the publication. But for monitoring, of course, these instruments that you install somewhere to monitor a landslide, a volcanic eruption, whatever, should be available at least to the monitoring institute in real time, so they can analyze the data or include it in their processing when it comes to like location of events or location of tremor or other like migrating sources. Of course, the kind of difficulty is if you have an event and if you add more stations to it, of course, it might affect your location. Like if there might be some bias, you might detect more events out of a sudden that is just linked to or caused by the increased number of seismometers. So in a way, this is something you need to keep in mind if if you add more stations to your network, that you will increase the sensitivity, you might detect lower magnitude events. And this is not because there are more events, it's just because you densified your network. So in a way, you also need to consider, does it make more sense to have like a continuous network throughout the time where you can compare your locations, or do you want to add more stations to have, much better catalog for this event? But I think it's that we should definitely move towards like an automatic processing, and not this, having different networks in the same location and the different groups working with different tools on it. But I think in seismology, for network-based analysis and event locations, I think we're at the point where we can just choose one and put all the seismometers together in a network and then do the location and the event analysis.
Thank you, Eva. So Gilda, I guess for fiber optics more challenging because it's pretty new.
Yeah, the main problem, I mean, it's an advantage and at the same time an advantage and a challenge, because due to the high spatial resolution and sampling rate, we have a huge amount of data. So 1.5 kilometer of fiber with a spatial resolution of 2 meters means 150 giga per day. Just 1.5 kilometers. So the main problem now is how to manage, not only for analysis point of view, but also to share this data. So if I want to share just a few days of data with the community, it's a real issue nowadays. So for other kind, for traditional methodology, there are several archives, IRIS, Orpheus, already developed and put in place. Maybe one way to cope with this is to follow the satellite community, because they have already since years cope with a very huge amount of data. And indeed, not only the satellite community provided the raw data, but also some product. So going to this website like Sentinel or others, you have access not only to the raw data, but also to some preliminary analysis that are very useful for researchers that would like to start to understand or investigate a particular area. So about fiber optic, we are at the beginning. So we have to find a way to share this data, and each device at this moment, so each interrogator has a different format. So there is a big work to do also for the fileization of the data in a way that the researcher could easily access to the data and work with them.
Thank you, Gilda. Yes, indeed, this is an issue. So this bring us to the question about the processing. How to get all this data, or if they are available, then people want to do something with them because they have a bright idea and they want to include this in their monitoring system or make a brilliant research on it. What are the new tools for data processing? Are there approaches that could be similar? So, for example, I will ask to Sabine to start. You mentioned that you cannot see on the ground if there are clouds. Are there any tools to remove the clouds, or any technique to get through the clouds and monitor 24 hours per day?
Okay, no, this with the cloud and optical remote sensing, I have to say, this is just a limitation. So no. And they will not be tools that allow to remove clouds. There are already some tools that allow to, maybe if it's like very thin clouds, we can work, but it's not like radar where you need to remove clouds and maybe you can still detect something. No, in the case of optical remote sensing, if it's too cloudy, it's just not useful data. So, but to answer your question, it's a very good question, because actually this has been a big development also, and EDMAP has got an open data policy, but also algorithm open data policy. That means that since 10 years we developed tools that actually they are all free and open software source. So they are FOSS softwares. And this has been an enormous development in the community also to provide all our algorithms on the web. So I will put a link in the chat on the Nmap toolbox. So that means everybody will be able to process the data. And from ESA, we can signalize. There are also plenty of tools. Sigrid already gave a link to the data, but there is also the ESA toolbox, the Snap toolbox. And also we should signalize the Google Earth Engine tools. Because if any of you, some people with the Google Earth Engine tools, you don't even need to download the data. You can make calculations and just process your result image. You don't have to download the data physically. That's a problem. It's also a problem of data volume. So those are, Sigrid already gave the links. There are big developments in this direction in the community for those free and open tools too. And I think this will be the future too.
Okay. So Gilda, machine learning, this kind of things? You are muted.
Yeah. So because of the huge amount of data,
yeah, exactly.
We have to see how also other community, I mean, the oceanography group, the astrophysics, they cope with this big amount of data. So the paradigm of big data could be exploited to analyze the data. And if the aim is the continuous monitoring, we have to approach this kind of methodology and exploit also the use of HPC. So what we need is not only to adapt the algorithm that are already available, for example, in array seismology, but also to implement new algorithms which are able to analyze the strain rate data as it is. So instead, not only adapting, but also try to extract as much as possible information from the high sampling rate in space and in time of the fiber optic data, using several kinds of approach that need to be investigated. So then to make available some tool, it will take time. So maybe in, I don't know, in 5 years we'll be at the same level of satellite community. I don't know. Let's see what the future will be.
So yeah, so it means that we have to teach all these algorithms and convince people. So maybe Eva, you have some ideas on this. You are a professor at university, so you may have some ideas. What are the tools that you are using to teach and call and make the students inclined to come to those fields that are very exciting, actually?
Well, I think in seismology we're lucky because about 10 years ago, some colleagues have started to develop seismology packages for Python. So they're open access, they're free of charge, and everyone can use them and contribute to it. So one of it is OpsPy, which the community uses, and another kind of development is Parocco, and part of Parocco are actually some really nice software tools where you can, for example, very easily open your waveforms and play around with filters and things. So you don't need to deal with all the theory, but it's a very easy access point for students to just play around and to get a feeling for earthquakes and do some processing in real time. So I think this is a very nice starting point and outreach thing that we use in classes actually as well. And so we're now pushing forwards to actually create a database for rotational codes as well, which have been developed. I mean, the theory behind it has been used in classical seismology as well, but still it has to be changed for the rotational seismology application. And yeah, we're now trying to make these open access so that if people are interested in rotational seismology, they have a starting point of code which has been tested on events that can be used and applied for any rotational data sets. And of course, same goes with the publication of these rotational data sets. It will be made open access alongside the publications or at some point, maybe just with the experiment so that everyone can access and use it and, look into other things, other interesting ideas people might have.
Thank you, Eva. So we just put some links in the chat so that everyone can have a look to it. Now, in the last the 4 minutes of this discussion, I'd like to try to make a link if there are no other questions from the audience, and to make the link between the what we have talked about, so the combination and the integration of data from the in situ and remote. We already touched this a little bit, but also there are the boreholes data. So how can we gather all this together? And maybe Kuo Fong will have some ideas on this, and she will probably give a hint of what she's going to talk about in the keynote for the SIM 3 and 4 together.
Yeah, thank you, Philip. Yeah, well, I learned a lot through this discussion, but I also in between of how much we can learn from I mean, for the future, and what we can learn from what we have now. And something I've been thinking is those low-cost sensors actually very good tools to deploy in a very wide region, and also go to borehole. Then we can really capture the source or the signal we intend to see. But the price, the cost is always one of the factors to decide what instruments to put into. So to between for the classic one to this big data for all the fiber we are going to carry on. I've been thinking what we want to explore for the new discovery. If we really want to have a new discovery, we cannot just rely on machine learning, because machine learning has to learn first. So I somehow in between, and in my career, I felt like, yeah, we want to discover the science, but in the same time, we want to also learn from the big data. So I'm torn in between, but I think maybe that's also important that we have the advanced one, but in the same time, we have classic ones that we can learn to, I mean, we can really have our scientific discovery through new data, but then have more data to really solve the problem. Well, yeah, that's somehow my comments, also the question to myself.
Thank you very much, Kuo Fong. Yeah, so we have 1 minute left in the time. So I would like to take the opportunity to thank you, all the speakers and all the people who contributed to this. And so, Paolo, I give you back the word to continue the program.
Yeah, I think now we need to move to the display room, if I'm not wrong, group display material viewing. Let me copy the link where, however, we will meet. So people,
Alex put it in the in the chat. Alex is the main manager of this conference. Thank you, Alex.
Thank you so much. Thank you so much. So I think there we will find also people from other group, and then at 10 o'clock GMT, maybe we will be back here, and Philippe will introduce the keynote speaker. And this will be the last part of this day.
Thank you all. Thank you, Paolo. So let's go to SIM 4 and 4 and to 7.
Yeah. I'm sorry, should we go to the group display or to the breakout rooms now?
To the Padlet, I think.
Okay.
Material viewing.